Welcome back to Beyond the Known, everyone. You've joined us for another deep dive in our Edge of Reality series.
Great to be here.
And today we're tackling something really fundamental, but also incredibly strange. The invisible universe, dark matter, and dark energy.
That's right. And it connects nicely in a way to our last discussion on quantum weirdness.
It really does. We talked about how the subatomic world just operates on totally different rules, didn't we?
Absolutely. Things like superposition particles being in multiple places at once, essentially.
Or entanglement, that spooky connection between particles no matter the distance.
And the observer effect, just looking at something changes it.
Right.
It's, counterintuitive stuff.
Totally. But as weird as quantum mechanics is, our research material for today suggests the universe on the grandest scales has its own deep, deep mysteries, things that are mostly invisible to us.
Oh, definitely. It turns out that everything we typically think of as the universe, stars, planets, galaxies, all the stuff that gives off light or that we can, interact with.
The normal stuff.
Exactly. Normal matter. It's only about, 4 or 5% of the total energy and mass content of the entire universe.
Wait, only 4 or 5%? That's tiny.
It is. The vast majority, like 95, 96%, is apparently made up of two things we can't directly see. Dark matter, which is estimated at maybe 23 to 27%.
Okay.
And the rest, the lion's share, around 68 to 73%, is attributed to something called dark energy.
Wow. So everything we see is just the tip of the iceberg. An almost entirely invisible iceberg. That's quite humbling.
It really puts things in perspective.
So our mission today for this deep dive is to try and unpack these invisible giants. We want to look at the evidence for them, explore what they might be, and maybe touch on what they mean for the universe's fate.
Sounds like a plan. Where should we start? Dark matter.
Yeah, let's start there. The research often mentions this idea of missing mass. What was the first sign something was, missing?
Okay, so the first real inkling that our cosmic accounting was off goes way back, actually, to the 1930s.
The 30s? That early?
Yep. An astronomer, Fritz Zwicky. He was observing the Coma cluster, a really big collection of galaxies.
Right.
And he noticed the galaxies within the cluster were moving around incredibly fast. Much faster than they should have been, given the amount of visible matter, the stars and gas he could detect.
So based on the gravity from the stuff he could see, they should have been moving slower, or the cluster shouldn't have held together.
Exactly the second part. They were moving so fast that the gravity from the visible parts of the cluster shouldn't have been enough to keep them bound together. They should have, escaped, flown off into space.
But they didn't.
But they didn't. So Zwicky proposed there must be some extra unseen matter dunkelmaterie, dark matter, providing the additional gravitational pull needed to hold the cluster together.
Okay, so that's Wiki in the 30s. But the research also really highlights Vera Rubin's work later on, in the 70s, right?
Absolutely. Zwicky's observation was maybe the first flag, but Vera Rubin's work provided much more systematic and compelling evidence. She studied the rotation of stars within individual galaxies, focusing initially on Andromeda, our neighbor.
And what did she expect to find based on, standard gravity?
Well, you'd expect stars further out from the galactic center, where the visible mass drops off, to orbit more slowly. Just like planets further from the sun orbit slower than closer ones. Gravity gets weaker with distance.
Makes sense. Less stuff pulling on them.
Precisely. But that's not what she found. Her measurements showed that stars way out on the edges of Andromeda were orbiting at pretty much the same speed as stars much closer in. The rotation curve, as we call it, was flat.
Flat, not dropping off like expected.
Not dropping off. And that was a huge problem. There just wasn't nearly enough visible matter, stars, gas, dust out there to explain why those outer stars were moving so fast they should have been flung out.
So, again, something unseen must be providing the extra gravity.
Exactly. Her work strongly suggested that galaxies are embedded in these massive, invisible halos of dark matter, providing the gravitational grip needed to explain those flat rotation curves.
Okay, so this invisible stuff, this dark matter, it's acting like a sort of cosmic glue, holding galaxies and clusters together.
That's a great way to put it, invisible glue. Without it, based on our understanding of gravity, these structures likely wouldn't hold together. Galaxies might just dissipate.
And it does more than just hold things together, right? I remember reading about a cosmic web.
Yes, that's another crucial role. Dark matter isn't just sitting passively in halos. It's thought to form this vast, interconnected network throughout the universe, the cosmic web, kind of like an invisible scaffolding.
A scaffolding, how does that work?
Well, the idea is that in the very early universe, tiny fluctuations in density were amplified more quickly in the dark matter because it doesn't interact with light and radiation pressure like normal matter does. So it started clumping together earlier, forming this web-like structure of filaments and voids.
And the normal matter followed.
Pretty much. Ordinary matter, the stuff we see, was then drawn by gravity into the denser regions of this dark matter scaffolding. So galaxies and clusters tended to form along the filaments of this cosmic web where the dark matter was already concentrated.
So the structure we see in the universe today, the way galaxies are arranged in clusters and filaments, that's basically tracing this underlying invisible dark matter skeleton.
That's the picture, yes.
Yeah.
It suggests dark matter wasn't just important for holding things together later,
Yeah.
but was absolutely fundamental for guiding how structures formed in the first place.
Okay, that's huge. So how do we actually detect this stuff if it's invisible? We mentioned Zwicky and Rubin inferring it from motion, but are there other ways? You mentioned halos earlier.
Right. One of the most powerful tools we have is gravitational lensing.
Ah, yes, Einstein's relativity kicking in. Mass warps space-time, and light follows that warp.
Exactly. Massive objects, including concentrations of dark matter, bend the fabric of space-time around them. When light from a very distant object, like a background galaxy, passes through or near one of these massive regions,
The light path gets bent.
it does. It acts like a lens, distorting, magnifying, or even creating multiple images of the distant object. By studying these distortions very carefully, astronomers can map out the distribution of mass, including the invisible dark matter that's causing the lensing.
So we can sort of see where the dark matter is by how it bends light from things behind it?
Precisely.
Yeah.
It lets us map the unseen. And the research material mentioned the bullet cluster, which is a fantastic example of this.
Right. Tell me about the bullet cluster. Why is it such strong evidence?
The bullet cluster is actually two galaxy clusters that have collided, or rather, passed through each other. What's amazing is that we can observe different components separately. We can see the galaxies themselves, mostly passing through unscathed. We can see the hot gas, which is the bulk of the ordinary matter in the clusters, using X-ray telescopes.
Okay.
And this hot gas from the two clusters clearly collided and slowed down, kind of lagging behind in the middle of the collision.
Like a big splash of hot gas.
Sort of, yeah. But then when we use gravitational lensing to map where most of the mass is...
Let me guess. It's not where the gas is.
Exactly. The lensing map shows the bulk of the mass stayed with the galaxies, moving ahead of the slowed down gas. This strongly suggests that most of the mass in the clusters isn't the interacting hot gas, but some kind of non-interacting matter, dark matter, that just passed right through the collision along with the galaxies.
Wow. That's a pretty clear separation, like seeing the ghost of the mass move through the visible stuff.
It's considered one of the most direct pieces of evidence we have that dark matter is real and behaves differently from ordinary matter.
Okay, so lensing, galaxy rotation curves, any other lines of evidence? The research mentioned the cosmic microwave background?
Yes, the CMB, that's the leftover radiation, the afterglow from the Big Bang. It's incredibly uniform, but it has these tiny, tiny temperature fluctuations.
Ripples from the early universe.
Essentially, yes. These fluctuations represent slight differences in density in the very early universe. Now, the pattern and size of these fluctuations, which we've measured with incredible precision.
Tell us something about dark matter.
They do. The models that best fit the observed CMB data require the presence of dark matter. Because dark matter could start clumping gravitationally earlier than ordinary matter, which was tied up with photons back then, it provided the initial gravitational seeds needed for structures to grow to the size we see today. Without dark matter, there simply wouldn't have been enough time since the Big Bang for gravity acting on ordinary matter alone to form the galaxies and clusters we observe.
So dark matter was essential for structure formation right from the beginning. It really is fundamental. Okay, so the evidence seems pretty compelling, but what is it? You said it's not just ordinary stuff that's dark.
Right. The evidence points away from it being things like planets, black holes, or just dim stars, stuff made of protons and neutrons like us. We call that baryonic matter. There just doesn't seem to be enough of that kind of dark baryonic matter out there.
So maybe Macho's massive compact halo objects, things like brown dwarfs or lone black holes, weren't they considered?
They were, and searches were conducted. While some Machos were found, they weren't nearly numerous enough to account for all the dark matter effects we see.
Okay, so if it's not normal matter, what's left? Exotic stuff.
That's where the leading theories are now focused. hypothetical elementary particles that aren't part of our current standard model of particle physics.
Stuff beyond the particles we know.
Exactly. The two main candidates that get talked about a lot are WIMPs and axions.
WIMPs, weakly interacting massive particles. The name kind of gives it away.
It does. Weakly interacting means they barely interact with ordinary matter, except through gravity and possibly the weak nuclear force. That's why they'd be dark. No electromagnetic interaction, no light. Massive means they'd have, well, a significant mass contributing to the gravitational effects.
And how are scientists looking for these WIMPs if they barely interact?
It's incredibly difficult. They use experiments often located deep underground to shield them from cosmic rays. Think of projects like CDMS or LUX or Xenon. They typically use large tanks of very pure material like liquid xenon or germanium crystals.
Okay.
And they wait, hoping that very, very rarely a WIMP from space will happen to directly collide with an atomic nucleus in the detector, depositing a tiny, detectable amount of energy.
Like looking for a needle in a cosmic haystack. Have they found anything definitive?
There have been some tantalizing hints over the years, some signals that looked promising, but nothing that's been definitively confirmed and replicated across multiple experiments yet. The search continues, getting more sensitive all the time.
All right, so WIMPs are a maybe. What about the other one you mentioned, axions?
Axions are another hypothetical particle, but quite different from WIMPs. They're predicted to be extremely light, potentially trillions of times lighter than an electron. They were actually proposed initially to solve a different problem in particle physics related to fundamental forces.
But they happen to fit the bill for dark matter, too.
Exactly. Their predicted properties, very weakly interacting, produced in the early universe, make them a viable candidate. Detecting them requires different kinds of experiment, often involving very strong magnetic fields, hoping to convert axions into detectable photons. That search is also ongoing and ramping up.
And what about neutrinos? We know they exist, they have a small mass, they're weakly interacting. Could they be dark matter?
That's a fair question. Neutrinos do contribute a tiny bit to the universe's mass density, but we know enough about their properties now to say they're just too light and they move too fast, hot dark matter, to be the dominant component. The kind of dark matter needed to form structures seems to be cold or warm, slower moving.
Okay, so the nature of dark matter is still a major puzzle. But its implications are huge, right? We wouldn't have galaxies without it.
It seems that way. Our research suggests it's fundamental to cosmic structure, and therefore potentially fundamental to our own existence on a planet orbiting a star within a galaxy. Understanding it could also revolutionize physics, pointing towards new particles and forces beyond the standard model.
Incredible. Something unseen shaping everything we see. Okay, let's shift gears then to the other big mystery. Dark energy. This is the stuff driving the universe's expansion to accelerate. That sounds completely backwards.
It really did initially. For most of the 20th century, the assumption was that the universe's expansion, started by the Big Bang, must be slowing down.
Because of gravity, right. All the matter pulling on itself should act like a brake.
Exactly. Gravity attracts. So everyone expected the expansion to decelerate. Maybe it would slow down forever, or maybe even slow down enough to eventually reverse into a big crunch.
But that's not what we found out.
Not at all. In the late 1990s, two independent teams were studying very distant Type Ia supernovae. These are incredibly useful because they are standard candles.
Meaning they have a known, consistent brightness.
Precisely. So by measuring how faint they appear to us, we can calculate how far away they are. And they also measure the supernova's redshift, which tells us how much the universe has expanded since the light left the supernova.
Okay, so distance and expansion measurements, what did they show?
They showed that the most distant supernovae were consistently fainter and therefore farther away than they should have been in a universe where expansion was slowing down.
Fainter means farther than expected. So the universe must have expanded more than expected to push them that far away.
Exactly. The only way to explain the data was if the expansion of the universe hasn't been slowing down, but has actually been accelerating over the last several billion years.
Accelerating. Wow. That must have been a shock.
It was a bombshell discovery. It won the Nobel Prize in Physics in 2011. It meant there had to be something overpowering gravity on cosmic scales, pushing things apart.
And that something is what we call dark energy.
That's the name given to this mysterious influence causing the acceleration. It's thought to be some kind of energy density inherent in space itself, acting as a sort of repulsive force or negative pressure.
So, completely different from dark matter, which clumps and attracts via gravity.
Very different. Dark energy seems to be smoothly distributed throughout space, not clumped up like dark matter. And its effect becomes more dominant as the universe expands.
Why more dominant?
Well, think about it. As the universe expands, the density of matter, both dark and ordinary, decreases because the same amount of matter occupies a larger volume. But if dark energy is a property of space itself, like an energy of the vacuum,
then as space expands, you get more space and thus more dark energy.
exactly, its density might remain constant or nearly constant. So, as matter thins out, the constant repulsive effect of dark energy eventually wins out over gravity on the largest scales, driving the acceleration.
Okay, that's weird. And didn't Einstein have an idea sort of like this that he later dismissed, his biggest blunder?
He did. He's one of the great ironies in science. When Einstein first formulated general relativity, the prevailing view was a static universe. To make his equations produce a static solution, he introduced a term called the cosmological constant, essentially an energy density of empty space that would counteract gravity.
A fudge factor for a static universe.
You could call it that. But then, when Edwin Hubble discovered the universe was expanding, Einstein reportedly called the cosmological constant his biggest blunder.
Because the universe wasn't static, after all.
Right. But now, with the discovery of accelerating expansion, something very much like his cosmological constant, a constant energy density of the vacuum, is actually the leading candidate for explaining dark energy.
So his blunder might not have been a blunder at all. It might actually be real.
It certainly looks that way. Dark energy could literally be the energy of empty space, which quantum physics suggests isn't truly empty anyway, but filled with virtual particles popping in and out of existence.
Mind-boggling. So if dark energy is real and causing acceleration, what does that mean for the future, the ultimate fate of the universe?
It paints a potentially bleak picture. If dark energy continues to dominate and acceleration continues, the most likely scenario is often called the big freeze, or heat death.
Big freeze.
Yeah. Galaxies would accelerate away from each other faster and faster. Eventually, distant galaxies would recede so quickly that their light could never reach us. Our observable universe would shrink, effectively. Within the remaining isolated galaxies, stars would eventually burn out, matter would decay, and the universe would become increasingly cold, dark, and empty. A long, slow fade into nothingness.
Yikes. That's depressing. Is that the only possibility? That the research mentioned a big rip?
That's a more speculative and, frankly, terrifying possibility. It depends on the exact nature of dark energy. If dark energy isn't constant but actually gets stronger over time, something called phantom energy, its repulsive force could eventually become infinite.
Stronger than gravity holding galaxies together.
Stronger than everything. It would first tear apart galaxy clusters, then galaxies themselves, then solar systems, then planets, and eventually it could overcome the forces holding atoms together, literally ripping apart the fabric of reality itself.
Okay, let's hope it's not that one.
Current observations tend to favor the cosmological constant model, leading towards the big freeze. But the nature of dark energy is still very uncertain. It's one of the biggest unsolved problems in physics.
So what could it be, other than the cosmological constant, the vacuum energy?
Well, some theories propose it might be a new kind of dynamic energy field pervading space, often called quintessence, which could change over time. Others wonder if maybe gravity itself works differently on cosmic scales than Einstein described, and maybe we need a modified theory of gravity instead of dark energy.
So it could be new energy, or it could be our understanding of gravity is incomplete.
Those are the main avenues of investigation, and huge experiments and surveys like the Dark Energy Survey, BISS, and upcoming ones like the Vera C. Rubin Observatory and the Roman Space Telescope are designed specifically to measure the expansion history and structure growth with extreme precision to try and distinguish between these possibilities and pin down the properties of dark energy.
It really is a frontier, isn't it? Trying to understand the fundamental nature of 70% of the universe.
Absolutely. Along with dark matter, it dominates the cosmos, yet we have so much to learn.
Well, this has been quite the journey into the invisible majority of the universe. We've covered dark matter, the cosmic glue, and scaffolding.
And dark energy, the mysterious force accelerating the expansion of everything.
The evidence seems strong, even if the actual nature of these things is still elusive.
It's compelling, yes. From galaxies spinning too fast to the accelerating cosmos, the observations point consistently towards these unseen components.
And it just hammers home that point. Everything we know, the atoms making us up, the stars, the planets, it's just a sliver, maybe 5% of what's actually out there.
It's a profound thought. The universe is mostly made of stuff we don't understand yet, shaping everything from the largest structures down to the ultimate fate of reality.
It really shows how much more there is to discover, doesn't it? What are these things? Are there new laws of physics waiting to be found? It's exciting, in a way.
Definitely. It drives so much cutting-edge research in cosmology, astrophysics, and particle physics. The quest is definitely on.
Well, thank you for joining us on this particular exploration right to the edge of reality. We really hope this deep dive sparked some curiosity about these huge cosmic mysteries.
It's been fascinating to discuss.
If you enjoyed diving into the invisible universe with us, please do like, follow, and subscribe to Beyond the Known. We'll have more deep dives into the biggest questions about the cosmos.
Keep questioning.
Absolutely. Until next time, keep looking up and keep questioning the nature of reality.